Hi, I'm Fabian.
I'm Elijah.
I'm Aaron.
This is the video report for Funduino 2 for Aerospace 304. Last time, we modeled the system dynamics and transfer function for a DC motor.
So in this one, we're going to use that model to design a PID speed controller to drive the motor to a target RPM.
And using that PID, we're going to implement it into Arduino to experimentally validate it.
To determine transfer function of the system, experimental measurements were taken. Before we dive into the software, let's take a look at the hardware. At the heart of the setup is Arduino Mega, which acts as the microcontroller that stores the control commands and sends power modulation signals to drive the motor. The entire system runs off a 12-volt DC power supply. To regulate that power and protect the components, particularly the Arduino, we use a L298N H bridge, which acts as a buffer, ensuring the motor receives sufficient current without overloading the microcontroller. Also, to prevent oscillating voltages and ensure stable operation, all components share a common ground. The Arduino communicates with the bridge to 3 control pins: a power modulation cable pin that connects to the L298's enable pin, which controls the motor speed by providing the duty cycle. Also, 2 additional digital output pins connect to the L298's input pins, which determine the direction of rotation by setting them to high or low in opposite states. On the feedback side, the rotary encoder sends position information with 2 signal lines to ensure that Arduino captures every pulse from the encoder without missing any steps, which is critical for accurate position tracking and closed-loop control.
On the software side, we had 3 scripts working together. But first, let me run through the analysis. The first thing that we did was take the 9.66 volts run from Funduino 1, because this is the case closest to 80% of our motor's nominal value, and we used that as our open loop plant. We also used the maximum RPM value from this run of 452.7 RPM as the reference omega for this project. We then closed the loop with unity feedback using MATLAB's feedback command with H set to 1. Closing the loop with unity feedback and no additional controller is essentially creating a proportional controller with a gain of 1. So at this point, we had a baseline closed loop system. We then plotted the step response of the system using the step command in MATLAB, scaling the system by the reference omega, since the input is no longer voltage, but a reference speed. We then used MATLAB's control system designer opened with the RL tool command to evaluate how the system would perform under the design requirements of less than 5 second settling time and less than 10% overshoot. From there, we decided on our own stricter requirements of less than 2 second settling time and 0 overshoot, and we designed a PID controller using PID tuning within the designer. The PID controller was exported as a MAT file so that it could be loaded directly into the analysis script without having to redesign it every single time. Now for the 3 scripts, the first of which is the Arduino code. It waits for a signal to start the motor from MATLAB and then enters a control loop that runs every 50 milliseconds. Each iteration, it reads the encoder position, calculates RPM, applies a low-pass filter to smooth out quantization noise, runs the PID calculation with the proportional, integral, and derivative gains calculated from the controller designed in the previous step, sends a PWM command to the motor, and then writes time, RPM, and error over serial. Next is the MATLAB read script. This script opens the serial port, sends the signal to Arduino to start, and then sits in a loop, reading the time, RPM, and error lines from serial and writing them to a data file which will be used for post-processing. And finally, the plotting and analysis script opens the experimental data file as well as the controller mat file and plots both the experimental run and the simulated run for comparison, extracting the performance metrics from the smoothed experimental curve.
I'm going to be reviewing some of the results we obtained over Funduino 2. So for the closed loop response, using the unity feedback and plugging it into the step response, we found this, which is approaching 1 since it is unity. And then putting the open loop transfer function into the root locus plotter with the requirements of a settling time less than 5 seconds and an overshoot of less than 10%, we can see that the gain value can be anywhere above k equals 0. And then looking at our actual PID function, you can see our setting of having to be settling time less than 2 seconds, which we came up with since it's less than 5, and we believe it is a fair amount to hit. And you can see that one of the closed poles is very close to this, but it is within spec slightly. And then using the control system we found with this, we can then get the simulated response and then compare it to the experimental response. And as you can see, they have these different shapes, though the settling time is about the same at 1.95 seconds. And we believe that this is the difference in these shapes is due to the static friction.
After evaluation of the dynamics of the system and the design of a controller, the PID can be implemented to the physical model of the DC motor. First, the Arduino code is uploaded through the Arduino IDE to instruct the microcontroller. After the uploading process is completed, MATLAB is used to actuate the motor and record data for post-processing. In this stage, the RPMs, the time values, and the error can be observed. So overall, we saw that the transfer function of a system can be used to model its dynamics and response to different inputs. Then we can use this to model a control system that will achieve certain performance parameters.
So we designed a PID controller in MATLAB with a proportional gain response to instantaneous error to drive the system toward the target RPM. The integral gain accounts for any persistent steady-state error, and the derivative gain smooths out the response by reacting to the rate of change of error.
Our performance requirements were a settling time under 2 seconds and 0% overshoot. Both of these were achieved with a settling time of 1.95 seconds. In addition, we also were going for a final value RPM of 452.7 RPM, and we got 453, so there is a negligible steady-state error there. And this small error is likely due to the control idealization